This video lecture is meant to cover the information from Unit 9, Section 2, which is all about enthalpy changes, but this video lecture covers some information that is not found in the Rosengarten curriculum. What we're going to be doing in this video lecture today is we will be finding the enthalpy change of a reaction from three different sources. The first source is very simply, you will access the information from either one of two reference tables. Reference table I, which is the one that you have on your handout on the right side, is called the heats of reaction at 101.3 kPa and 298 Kelvin. These are standard conditions when measuring chemical reactions. So what you can see here, table I, you've used this before, various reactions. The top the top six reactions, actually the top six reactions are all what we call combustion reactions. Then the middle section are all formation reactions. The formation reactions, if you read them in the reverse, would be decomposition reactions. And if you reverse the reaction, you would then reverse the sign of the enthalpy, the delta H. And at the bottom, you will see the enthalpies of substances as they dissolve in water. The table on the left, reference table B in the advanced enriched section of your reference tables, has two columns: an enthalpy of formation, delta HF. This is the column we are most interested in at this point in time. And the other column, free energy of formation, is something we'll be studying later on in this unit. Right? So if the enthalpy of formation represents how much energy is either released or absorbed when the compound is formed directly from its elements. I'll say that again. The enthalpy of formation is the energy absorbed or released when the compound is formed directly from its elements. Again, a negative sign implies it's an exothermic formation. If it's a positive sign, it means that the formation of that compound is endothermic. The second source that we're going to look at for finding enthalpy changes is when we combine these heats of formation of the compounds in a reaction. And the third source will be when we combine equations using something called Hess's law. So the first strategy, looking up from the tables, we're not going to spend much time on that because you just refer to these tables and you find the information that is being requested. So if you turn to page 2, we'll be taking a look at heat of formation and using those to find the enthalpies in a chemical reaction. The heat of formation, as I said earlier, is the energy absorbed or released when a compound is formed from its elements. It's measured at standard conditions, 1 atmosphere of pressure, which is the same as 101.3 kilopascals, and 298 Kelvin. Not really too much you have to do with that other than just recognize that those are standard conditions. The heat of formation is symbolized as a delta H with a little circle symbol followed by a subscripted F. The circle means it is at the enthalpy has been measured at standard conditions. The F stands for formation. Couple things you need to know. Elements have zero enthalpy of formation because by definition the enthalpy of formation is how much energy it takes to form a compound from its elements. So it stands to reason that elements can't have a heat of formation. So anytime you see an element in a chemical reaction, just assume that it will have zero enthalpy of formation. You'll also need to know to look up in AE table B to look up the enthalpy of formation for compounds if the enthalpies are not given to you in a particular problem. You will use the heat of formations from table B to find the heat of a reaction by using this equation. Be sure to multiply the enthalpies of each compound by its coefficient that you see in the balanced equation. Okay, so there's two things going on here. We have a mathematical equation that you see here, delta H of the reaction. The enthalpy of the reaction is equal to sigma. This sigma right here is, that sigma, just means the sum. So you're going to take the sum of all the enthalpy of the products, and you're going to subtract the sum of all the enthalpy of the reactants. But this is what this statement right here is trying to emphasize, that if you have a coefficient in front of one of your reactants or one of your products in the balanced chemical equation, you will need to factor that into the enthalpy, because enthalpies of formation are given per mole. So if you have 2 moles of something, you'll have to multiply the enthalpy by 2. Right. So I think the best way at this point to get this started is to jump into a couple of problems. This first problem says to determine the enthalpy change for the following reaction. We have calcium carbonate decomposing into calcium oxide and carbon dioxide. It says given that the heat of formation of calcium carbonate is negative 1,207 kilojoules per mole, and the heat of formation of calcium oxide is negative 636 kilojoules per mole. All right, so we're given information about calcium carbonate and calcium oxide, but we are not given information about carbon dioxide, which means hopefully we can find that information on one of our reference tables. So the first thing we're going to do is identify what we have been given in the problem. So calcium carbonate is negative 1207 kilojoules. So I'm going to put that number right up here just to help me keep track of all of this information. The calcium oxide is negative 636 kilojoules per mole for that 1 mole that's written in there. And carbon dioxide, not given to us, but if we go back and look up carbon dioxide in AE reference table B, carbon dioxide is about the 5th or the 6th compound down, and the enthalpy of formation is listed as negative 393 kilojoules. Okay, so now that we have all the enthalpies of formation, we can go ahead and substitute it into our equation. So the heat of the reaction, the delta H of the reaction, is equal to the enthalpy of all the products added up, and then we will subtract the enthalpies of all the reactants added up. So here's how we're going to do this. So the products, the first product is calcium oxide, which has a negative 636 kilojoule enthalpy. And then we are good. This is the sum of all the products. So now we have to add the other product, which is a negative 393 kilojoule enthalpy. Okay, so right there in brackets, that represents all of the enthalpies of our products. Now we are going to subtract out the enthalpies of our reactants. And we have only one reactant, and that has an enthalpy of negative 1207 kilojoules. Okay, so now it's just a matter of manipulating the arithmetic. When you add a negative number, you are of course really just subtracting it. So negative 636 minus 393 works out to negative 1029 kilojoules. I'm going to keep that in brackets for the moment. And then subtracting a negative, of course, what you're really doing is you're adding that number. And so what we are doing is adding 1207 kilojoules. All right, so we have the sum of our products and the sum of our reactants, and ultimately we were supposed to be subtracting them, but subtracting a negative makes it an addition problem here. So when we add these two numbers together, what we see is that the heat of the reaction ends up being a positive 178 kilojoule enthalpy. Okay, we didn't have to factor in any of the coefficients in this particular example because the coefficients were all 1, and so we'll see that factor in a couple of problems here. Let's take a look at problem number 2, which says that carbon tetrachloride can be formed by reacting chlorine with methane. We have CH4, that's methane, reacting with 2 moles of chlorine gas to form 1 mole of carbon tetrachloride and 2 moles of hydrogen. Given that the heat of formation of methane is negative 75 kilojoules per mole and the heat of formation of carbon tetrachloride is negative 135 kilojoules per mole, determine the heat of the reaction. So we're not given any information about chlorine or hydrogen, And you're not going to find them in any of your reference tables because hydrogen and chlorine are both elements. And elements can't have a heat of formation, so we say that their enthalpy of formation is just 0. We do know that methane is negative 75 kilojoules, and we know that carbon tetrachloride is negative 135 kilojoules. So once we've got that identified, it's really just a matter of plugging those numbers in. The heat of the reaction is going to be the sum of all the enthalpies of the product. Okay, well, there's only the one at negative 135 kilojoules. And we are going to subtract out the enthalpies, the sum of all the enthalpies of the reactants, which this one's pretty straightforward. There's just the methane at negative 75 kilojoules. And so now it's just the arithmetic of adding up all of these numbers. Right? Subtracting a negative really means you're adding that number. So negative 135 plus 75 works out to a heat of a reaction to be negative 60 kilojoules. The next problem reads, when potassium chloride reacts with oxygen under the right conditions, potassium chlorate is formed. Given that the heat of formation of potassium chloride is negative 391 kilojoules per mole, determine the heat of reaction. All right, so what do we know about this equation? We are given that potassium chlorate has an enthalpy of formation of negative 391. So I'm going to put that right above the potassium chlorate. Oxygen, an element, will have 0 enthalpy of formation. We're not given any information about KCl, potassium chloride, so we're going to need to look this one up. KCl from AE, reference table B, has an enthalpy of negative 436. These are all in kilojoules per mole. Okay, now this reactant and this product both have coefficients of 2's, so we're going to need to factor that in this particular example. So here's how this works. The heat of the reaction is equal to the sum of all the products' enthalpies. So let's see, we have negative 391 kilojoules for the enthalpy of our product, but we're going to multiply that by 2. That's our only product, so we don't have to add any other number to that number. We have one reactant, it's KCl, so we're going to subtract out the enthalpy of 2 of these, because there's a coefficient of 2 in front of the KCl, times the negative 436 kilojoules. So now it's a matter of arithmetic, plugging these numbers into your calculator. 2 times negative 391 works out to negative 782 kilojoules. We're going to subtract out 2 times negative 436, which works out to negative 872 kilojoules. Now it's just a matter of making sure that we add that number. So negative 782 plus 872 works out to the heat of the reaction being a positive 90 kilojoules. All right, I'm going to let you try numbers 4 and 5. I will post the answers to these, but let's see if you can accomplish the same answer that I show you here. The correct answer for number 4 works out to a heat of a reaction of negative 1,136 kilojoules. And for number 5, the heat of the reaction works out to be negative 476 kilojoules. All right, that one's definitely probably the trickiest one of the lot. Let's see what you can do. And I'm actually going to end the video here, and I'm going to pick up with a second video to go over the Hess's Law problems. So take some time to finish these 2 problems. See me if you have any questions, and then go ahead and take a look at the Hess's Law video separately. All right, see you in the classroom.